Hello friends, this video on equilibrium part 6 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 5. To start understand the equilibrium, the first law that we should know is the law of mass action, which says that at a constant temperature, please note the temperature has to be constant, the rate of chemical reaction is directly proportional to the product of the molar concentration of reacting species with each concentration term raised to the power equal to the numerical coefficient of that species in the chemical reaction. For example, if I have X of A and Y of B, they react to give some products. This one. So the rate will be directly proportional to, so I have used some constant here, A to the power X into B to the power Y. This is what my law of mass action says. So if you, instead of reading the 3 lines, you can see that if I have some reaction where X mole of A and Y mole of B give me some product, so the rate of this reaction, the forward reaction, I'm talking about the forward reaction, only the rate of this forward reaction will be directly proportional to A times X into B to the power Y. This is my law of mass action. So now law of mass action will be using to find the law of chemical equilibrium. So equilibrium mixture is nothing but a mixture where the reactants and the products are in the equilibrium, and there you have the rate of forward reaction is equal to rate of forward reaction. So we have my equation here, the equilibrium reaction here. A mole of A plus B mole of B gives C mole of C and D mole of D. So for this, the forward reaction will be what? Rate of forward reactions will be some constant Kf into A to the power small a into capital B to the power small, right? This will be the rate of forward reaction, because I'll assume that this is nothing but some product. Similarly, for the backward reaction, if I assume that C mole of C plus D mole of D gives some product, this is the backward reaction, right? This gives this. So for this, the rate of backward reaction will be some constant into capital C to the power small c into capital D to the power small d, right? Now I say that in equilibrium the rate of forward reaction is equal to rate of backward reaction. So I can say that the rate of forward reaction, this value, this guy, is equal to rate of backward reaction, this guy in the square. So both are equal. So if you equate this, you will see that there is something called Kf by Kb, and that is also constant because constant by constant, and that is equal to this. This whole thing will be constant. That is nothing but the product C to the power molar concentration of C, product D to the power molar concentration of D, product A to the power molar concentration of A, product B to the power molar concentration. So C to the power C, D to the power D, divide by A to the power A, B to the power B. This is my equilibrium constant, and that is denoted by Kc, equilibrium constant, right? So we got this Kc from the law of mass action. So for any reaction, AA plus BB is equal to CC plus DD, my Kc will be C to the power C into D to the power D divided by A to the power A, B to the power B. So with this, we have this law of chemical equilibrium defined that says that at a given temperature, please note temperature is a critical factor here, the ratio of product of equilibrium concentration to the product of reactant with each concentration term raised to the power equal to the respective stoichiometric concentration in the balanced reaction has a constant value. Correct? Let me repeat. At a given temperature, the ratio of the products of the equilibrium concentration to that of the reactant, and each of these raised to the power of the stoichiometric coefficient is a constant value. This is nothing but my law of chemical equilibrium. So we'll discuss something more about laws of chemical reaction, equilibrium. The equilibrium constant of the reverse reaction will be inverse of the equilibrium constant of the forward reaction. Makes sense, right? For example, Example, I have AA plus small b gives small c plus small b. So forward reaction, I will be equilibrium coefficient will be this guy, capital C to the power small c, capital D to the power small d by a to the power small a, capital B to the power small. This will be the forward reaction. If we reverse this reaction itself, the reverse of this will be what? Capital A to the power A, capital B to the power small b by capital C to the power small c, capital D to the power small d. Right? So if you see, both are reversed actually. K and K dash. Also, if you change the stoichiometric coefficient of a chemical reaction and multiplying throughout by a factor, the equilibrium constant also changes. For example, if you see, this is my chemical reaction, A and B, like this, yeah, AA plus BB gives CC plus small dd. So in this case, if Kc is my equilibrium constant, the value is I've given here, just write C to the power small c, D to the power small d by A to the power small a, B to the power small. So if you just flip this equation, you see my reverse reaction, equilibrium constant becomes 1 by equilibrium constant of forward reaction. Also, if you see, in this case I have multiplied n. I have multiplied n actually in the forward reaction, also in the backward reaction also. So if you see, my K dash C becomes Kc to the power n. Why logically also, if you see, it will be now C to the power nc and D to the power nd. Here it will be A to the power na and it will be B to the power nb. So if you take n common, so this becomes C to the power C, D to the power D, A to the power A, B to the power B, to the power n. And that is nothing but K to the power n. Correct? And that's what I'm trying to do. Correct? So now we have learned equilibrium constant. So let's understand steps to write equilibrium constant for a given reaction. First step is write the equation for the reaction. Once you are done with the equation of the reaction, write the product of the equilibrium, concentration of the product in the numerator. You omit the solid part, pure solid, pure liquid and pure solvent part. Why? Because see, everything I will be writing in moles per liter. So moles per liter for pure solid will be constant, right? Pure liquid also will be constant. Only for the gases or impure substance, this value will change. For example, I have calcium. For calcium, moles per liter will be same. You take any calcium. If you take let's suppose iodine, or iodine gas, moles or iodine, if you take iodine gas, then moles per liter will change. It may depend on the volume of the flask, but for iodine liquid, the moles per liter will be constant. So since they are constant, we omit those parts. We'll discuss more on this in the next slide when we talk about this question. And same thing we do for the product, the reactants, right? And here also we omit the pure solid, pure liquid and pure solid, because for them the moles per liter part is constant. And raise the concentration to the power of the stoichiometric coefficient. So we'll do for all these reactions, we'll see how it looks. For example, for this reaction, this guy is pure solid, we'll ignore, pure solid ignore. So here the Kc will be CO2 to the power 1, because it is to the power. You'll ignore these two parts. Here if you see pure solid, you can ignore. So here Kc will be Ag plus and Br minus. So when it is an aqueous or when it is gaseous phase, the moles per liter part may vary, right? So for example, the same Ag plus ion, if I am putting in 1 liter, and the same number of Ag plus ion, if I am putting in 10 liter, the moles per liter will change. And that's why we have to write it. But for solid, for example, CaCO3 calcium carbonate, if I put this in 10 liter solution or if I put this in 100 liter solution, it doesn't matter because moles per liter will be same, right? Because we'll talk about the volume of calcium carbonate, the volume which it occupies, right? We'll not talk about the whole volume, correct? Because calcium carbonate will be in the small volume, even if it is a big tank. Then we'll talk about this small volume. So let's talk about this CH3COH from liquid to gas. Also pure liquid, we can ignore this. So Kc becomes CH3COH gas. Correct. So how do you do that? So you first write the concentration of the product, divide by, actually there was no reaction where I could get this, divide by concentration of the reactant, and each of this to the power of the stoichiometric option. I think we'll take some examples in this, we'll understand how to write this case. It's a very easy thing. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.